All right, I hope you guys can hear me and see my screen. Um, so, um, all right. So yesterday we started talking about activation functions. So basically, we have the activation function. The main purpose of the activation function will be to uh, so basically we when whenever you have a neural network, so we have the information from the previous layer multiplied by the weight, and the sum of all the weight that will be applied there plus a certain bias will give the output inside the next layer here. But before we get in the next layer, we apply an activation function which will convert that value into a certain value in a certain range. So different activation function will have a different way of converting those information or the output from the previous layer. So if we have a sigmoid function or a softmax function, they will all uh, convert to in a different way. But most of those functions, like when you use the sigmoid function, you end up having a vanishing gradient problem. So to avoid a vanishing gradient problem, the best way is to use an activation function such as the ReLU activation function. So the ReLU will be a very good activation function. We also spoke about optimizers. We have the Adam optimizer, the Ada grade optimizer. Okay, so when we're designing a neural network, what we mentioned yesterday, the input layer must uh, must have the numbers of neurons in the input layers uh, is the same as the numbers of features that are going to use to train the model. Um, and then the output layer in a classification problem, the output layer will have the numbers of neurons will be the same numbers of outputs that we are expecting. All right. So generally, the more layers we have, the more accurate the system is, but we can also create an overfitting problem. And to avoid that, we need to do a proper research in terms of how many layers we will need for that. So, and then yesterday we spoke about what you call this, the normalization. Okay, I was actually supposed to prepare that. Okay. So we spoke about normalization. So when we talk about normalization, so we have. I'm just going to try and show you an example of normalization. So normalization is basically what we have. Yesterday, I've mentioned that sometimes the type of data that we have, there's a very big difference between those those data. So basically, we have some data. Let's say you are using an age. The age of the person is around 30, but when you are using another feature, is maybe uh, the the weight of the person. So because of that, the weight of the person may be a problem because we now get to a point where we have data that are in different ranges. Okay, so I'm trying to, okay, in the meantime, when that is opening, I'll show you an example of normalization, but in the meantime, okay, I think it should be ready somehow. Um, Let me see if it's the right one. Yeah. So in the meantime, when I'm looking for that, okay, so you need to know normalization, because yesterday there was someone who said they don't understand what is normalization. So normalization is just a process of introducing a way of controlling the range of the data. So we basically look at the range that we have, and then we're going to normalize this data. That means we're going to convert everything in a certain range. So we take every feature that we have, we're going to say all the features will be in a space of maybe 1 to 2, or 0 to 2, or 0 to 1, so that everything has the same what you call that, so that everything has the same range. What's going on here? Oh, all right. So is there so anybody who still doesn't know what is, who still doesn't understand what are the concepts behind normalization? Anybody who still doesn't know? Okay, so everybody understand that. Okay, guys, it looks like I'm not getting what I needed. Um, I need the data. I'm not getting the data here. It's not loading. Okay, that's fine. We'll look at it later. Can move on as long as you guys understand normalization. So yeah, that should be fine. Okay, I think I have one example here. I'm just trying to see if I'm checking the codes to see if there's any. Okay, anyway, let me share this. Let me share this page so we see this is one of the example of the models. This is for text classification. So basically, we're trying to read certain text. So this is the text classification model. Okay. Um, so when you look at it, let's see here. Obviously, this is where we're going to have the data. How we're going to split. So we have the uh, data. We will have the training and testing data, and the batch size will be 1, which means that we're going to use um, all the data at the same time, all the samples when the model is changing the weight. Remember when we talk about gradient descent, we said if we use a certain batch size, it means we can use a mini batch gradient descent or a stochastic gradient descent there. So this is just to show the data. Okay, and then we have to build the model. So here we downloaded this data here. So basically here we build the model by the syntax. So when we build the model, we have the inputs layer. So the first layer will be this, what is app layer. app layer is right here. So this is the input layer. So the input will take exactly the amount of features there. That's why we left it empty here. So it has words in it, right? We have that, and then we will have the next layer, which will be, we'll have 16 node neurons. The activation function that we're going to use will be the ReLU here. And then the last layer will be we'll have one output. So you look at this problem, we have one output there. And then in terms of optimizers, we use the Adam. Remember, guys, what I said to you yesterday, there's no need for you to memorize those formulas. So the optimizer here, we use Adam. The loss function, we use a binary cross entropy function. So the cross entropy, because we are dealing with a classification, and then we're going to measure the accuracy here. Okay, so to validate the data, so out of the data we're going to train 10,000 data, and then there is data that we're gonna use for validation, so some of the data, and then the model has been trained. In this case, we use a batch size of 512. That means out of all the data that we use, we're going to divide by 510. That's the amount of samples it's going to be changing the weight at this at each iteration. So, and then we have this at the epoch. Epoch is the amount of time we're going to train this model. All right. And then we can evaluate the model here. So, okay, and then we just measure the whatever accuracy and everything that we can. Let me just run it. Hopefully, it's going to download the data and form that. Okay, so in this case, this is a model because we are already downloading this data. We're going to see when they display, and then we're going to see. Let me see here. Okay, so running. Okay, so in this scenario, we basically have these data. We're gonna see them. So the data are just kind of sentences that represent certain movie reviews. So it's the review that people gave for these movies, right? So people gave some reviews about these movies. So basically, what we have for this data is we have to classify movies review as positive or negative using the text of the review that people gave. So this is just a binary classification problem. This is why we've used the binary cross entropy as the activation function. So the data sets that were given to us, the IMDb data set, will contain the text of 50,000 movies from the Internet Movie database. Okay, so they are split into 25,000 reviews for training and 25,000 for testing. So the training and the testing sets are balanced, meaning they contain an equal number of positive and negative reviews. Okay, so now we have this note here. So the first step, we have set up that. Okay, so here let's check the data separated by 25,000 and 25,000. Okay. Okay, so you can see here we have about 25,000 for training and 25,000 for testing. This is also one of the best methods of writing a proper model, because if you have the same amount of training and testing, then you're going to have a very good accuracy. because you can evaluate your model properly than just having a few for testing, but you have many for training. Okay. Okay, so these are the sentences. As you can see, there is so many sentences. There is about 50,000, you know. So here we're just going to print about 10 of them. So these are the data. So all these sentences here are going to be put into the system. So the system will learn from that and understand certain review and see, okay, this review were positive or negative. So you look at this, for example, here, the output where we have 0, 1, the 0, 0, that means negative, negative, positive, 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 negative. So those were the 10 reviews here. And then we built the model. As you can see, the model. So yes, this is exactly what will happen. So as you can see, the model had sentences. So we had these sentences, but as you can see, the model has converted those sentences into numbers. Can you see? They are now representing numbers for the model to do the mathematical calculations. So if we keep them as words, they will mean nothing. So that's why we have to represent them as numbers. So that is part of what we call normalization. So that can be a way of normalizing. So normalization can be either something like changing the data type. It can be converting to a certain the same units. It can be changing. Maybe you're dealing with pictures. You have different shapes or different sizes. It can be getting the same size. All right. So that's how we're going to have that. Okay. So if we look at okay. So some of the acronym that we spoke about, ANN, will be the artificial neural network. That means those are the neural networks that we have in AI, which imitate what the human neural network does, the biological human, the neural network that you have in your brain where all the information are connected and put inside a certain network, all right? So the same thing happened in computers. And then we have the MSE, which is the mean square error. So this is a loss error that we use in order to reduce the loss, which means the inaccuracy of the model, all right? This is used mostly when you're dealing with a regression problem, which means that the output of your research can be any type of value. But when you're dealing with a classification problem, we use the CE, which is the cross entropy. If there's only two options, true or false, male or female, if it's a binary classification you're dealing with, you can use a binary cross entropy. Okay. And the BGD is the batch gradient descent, which is a type of gradient descent. In order to reduce the loss, we use the gradient descent method. Batch gradient descent means that every time we're going to take all the samples and change the weight. That's what the model is going to do while training. But the stochastic gradient descent, it means it's going to take one sample at a time. And the mini batch gradient descent, it's taking a certain group of samples at a time. All right. So that was kind of the introduction of neural networks. Let's move to image processing and applications, right? So when we talk about one of the most used way of building models is dealing with computer vision. So computer vision is playing a big role, is one of the technology that is really advanced today because you're dealing with everything about facial recognition, all this system that has to do with images, analyzing images. So you can see AI is really being used in this area. Okay, so when you look at neural networks, you have many type of neural networks. So if you looking at image recognition, you have the CNN, convolutional neural network, which is specialized for the convolutional neural network is specialized for image recognition. So when we're dealing with image recognition, you must know the neural network that we need to use is the convolutional neural network, because computer vision is one of the most used technology in terms of your AI. So it works just like human beings. So if we show you a face of a person, we hide everything. We only show you the eyes of the person. It may be difficult for you to detect who is that person. But the more information we're giving you, the more you are creating the full picture of the person, right? So computer vision is all about analyzing videos, images, and try to predict and try to classify those images and videos. So when we will deal with like analyzing videos from a mall and detecting intruders or suspects of a certain crime, that will work with computer vision technologies. So right, so we're gonna have to implement these technologies in order to build this AI tool that will work in this case. So certain application scenarios where you're going to use computer vision will be like in public security protection, right? Because we're going to have to deal with object detection, fingerprint recognition, environmental modeling, understand? So in biomedicine, so where we can do certain analysis on the X-rays and that. So if we looking at, I've had a conversation with someone. I said, in just a few years, a lot of AI's tool will replace doctors. And this person told me, no, it's impossible for a doctor to be replaced by an AI because this doctor went to university, I don't know, for 7 years, 8 years. And then I said, that doctor, when they went to university in the first year, they didn't know anything. So everything they have learned it from books and from the knowledge that they got. That's exactly what an AI can do. The AI can also learn from the same books and from the same knowledge. And the AI is going to be better because the AI is not going to forget anything. But the doctor forgot everything they've studied in the first year. This is why none of us will need to do a surgery, get to the hospital, they tell you this doctor just graduated. You know, you're not going to agree with that doctor. I don't know. Is there anyone who will be okay with a doctor who just graduated to perform a surgery on them? No. Why? Because you know that these doctors still need experience. What is experience? Experience is not just they have to learn new things. No, experience means that whatever they have learned, they have to remind themselves and they have to apply it. So now computers can do that better because computers do not forget. So we can basically teach what we do here with X-ray, for example, is we can provide certain data, certain images of certain medical conditions that were taken. So we have many images for a certain tumor, for example, and then we let the AI understand the pattern, understand those images, so that the next time you have a scan result, you can just show it to the AI, and the AI can confirm if we are dealing with the same condition. All right, so computer vision really apply in biomedicine. It apply in word processing, where we have to actually get character recognition, recognizing. You have it, for example, today when you're trying to scan some document, they just tell you, you put your ID there, you scan your ID, it's automatically pick up those information written on your ID. So those are examples of word processing. So it pick up those information and do that. Okay, so we have it in smart transportation. where we're gonna create, where we have in many countries you have road traffic management. So the cameras in roads can see how the traffic is, if it's if there's so many cars or less cars, and the robot can decide how long it can take to change from one color to another color, instead of us having robots that take the same amount of time. I'm sure many of us have driven to some road. When you get there, there's no cars on the other side, but you feel like the robot is taking too long. Why? Because that robot has been set. If it has been set to change after 2 minutes or 3 minutes, it's going to wait for 2 minutes, 3 minutes, even in the middle of the night. And you will see, for example, in South Africa, we have a system where every time you're driving at night, you get by the robot. If there's no cars, if you feel like it's safe, you just drive off, even if the robot is still red, which is very dangerous. You understand? But if you have smart transportation, which means that the robots are equipped with material that can detect the traffic and see if the robot is red and you arrive there, there is no other cars on the other side, it's safe. The robot turned green. You understand? So things like that can really help. Right. So you have it in entertainment with movie effects, video editing. Today, you don't really need to be cutting video. You cut, you paste here. Today, you have a lot of AI tools that can actually detect images in those videos and edit it. Right. So everything is easy with today's technology. All right. So the 3 R's of computer vision. We have image recognition, right? Which will have to do with classifying images. So an example I can give you is we have pictures of cats and pictures of dogs. We train the model to understand the pattern, to understand how does a dog look like, how does a cat look like, and then the machine can be able to do image classification, right? And by recognizing the image. And then we have image reorganization, right? So this can help in terms of when you have certain images with different sizes, so the model can really help you arrange that. And then we have image reconstruction. So this is from different dimension of images, um, and then the image reconstruction can reconstruct the image. So that can happen in many cases. For example, you scan, you have some images that were scanned, but they were not completed. So the image reconstruction can reconstruct the rest of the image. So that's that is how computer vision. So when we talk about the 3R, we talk about image recognition, image reconstruction, and image reorganization. All right. So computer vision is really there's a lot of fields that really get involved in computer vision, right? So you have, for example, neuroscience. So neuroscience, how does neuroscience comes in this? Because we understand the same way the brain works, we try to imitate the same strategy and create algorithm for computer vision, right? So you have all the graphic algorithm, uh, information retrieval, machine learning, robotics, speech, natural language processing. So you have many disciplines that get involved there, from many science such as biology, physics, engineering, mathematics. So all these come together to create these tools that will be applied in computer vision technology. You understand? So where we can have, I think when we were doing the AI class, we done an example of this where we have an image and then we use a model that will be able to detect object in the image. All right. All right. So digital image processing, this is how the human, so when we have human eyes, so the images that human can see are just reflection, right? reflection. First of all, there need to be a reflection of the light. So if that's the reason why in the dark you can't see, it doesn't mean your eyes don't work anymore. Your eyes still work the same, but you can't see in the dark. Why? Because your eyes are not reflecting the light. So your eyes need to find a source of light and reflect that light toward a certain object. Then you can see that object. Then your brain can say it can see the object. So when we look at the light energy, which is identified by the eyes. So that's light energy. The eyes detect that light and transfer that light to a certain object, right? So that's how we can be able to see. So that's how the lights will enter the human eyes, which will allow the object to be seen. So now, when we do that now in computers, so what we can do is that we can use kind of a function of XY to represent an image. So which is like a vector, which consists of two parts, right? So we have the light source component emitted to observe the scene, and the light source components are which reflected by the object in the scene. And then we have the size of Ix, which is the Ix is, remember, is the light source component. Okay, so the size of Ixy is determined by the illumination source. Okay, so this is how we're going to actually represent it. So we do exactly the same thing that we're going to do. So from next week, we're going to be using Huawei softwares to try and design this, because that will help you in your as we move forward. Okay. So any questions so far, guys? Any question? Any question? Okay, so what I was saying, the same way the eyes will convert, will reflect the light on the object, the same way as well, cameras have been created, right? So basically, to get an image, what will happen is it's a process that is similar to the process that is used by human eyes, right, to generate all the images. So basically, to acquire a certain image, what the device need to do is we need to input an electrical energy with the photoreceptive sensor material, which is on that device. So now that will convert that input energy into a voltage. And then that voltage will be quantified, resulting into a voltage wave that will obtain a digital image. So the numbers of sensors, dimensions, and sensing capability of the sensor will determine the quality of the image. That's why you will find we had cameras that have a very bad quality, and then we have cameras that give you a very good quality. Okay, so the same image can be taken with a different camera, and then it gives you a different image. All right, guys. All right, guys. So this will be all for today and for this week. We will pick it up next week. Any question?
So, sir,
Yes.
I've heard you have mentioned some softwares to do the actual practicals. So, do you need to install those softwares, or you'll be using them demonstrating me.
No, I'm gonna demonstrate. I'm gonna show you. Yeah. Any other question? All right, guys. If there's any other question on anything, you can always, if you think on the group, maybe I may not see it, you can send me a private message. That's fine. All right, guys. Have a great evening and a great weekend. I'll see you next week.